Hi, and thanks for having me. You've heard, my name is Helge, and as of this month, I'm a full-time freelance astrodynamicist. Hold that thought. However, for the past 2.5 years, I've been a part-time freelance astrodynamicist, working for LSF, the Libre Space Foundation, which is a non-profit from Greece, furthering the use of open hardware and open software in space. And through some twists of fate, I became LSF's tech lead for Murphy's Law, the project, also known as Ephemerista. So the mission was to develop a new open source mission analysis simulator for telecommunications constellations based on existing open source technologies for ESA, the European Space Agency, and do it in 18 months. And as I foreshadowed, things did not go to plan. So one of the main requirements was to provide a Python API, and thus we chose Polyastro, the leading open source astrodynamics library in Python, as the centerpiece of our implementation. We also had the current maintainer and the former maintainer and creator of Polyastro on the team. Everything was great, and in August 23, we were in month 6 of our 2-month requirement analysis phase, and then this happened. Insert your favorite curse word there. In short, Polyastro's creator rage quit the space industry completely for very good reasons. I mean, maintainer burnout is a real thing. The current maintainer of Polyastro was barred on working from it further because his employer saw a potential conflict of interest, and he was not allowed to work on open source in general anymore in that space. And so our team suddenly missed 2 key people and a main dependency. After some consideration, we decided that taking over maintainership or forking was not really an option due to lack of knowledge of the code base and the size and age of it. And we started to look into alternatives and ended up with this choice. So, show of hands, would you A, use the industry standard Java library? Or would you B, rewrite it in Rust? You folks are insane, I like that. So, spoiler, we did both. And I want to give you some context so you can make an informed decision. First things first, what is space mission analysis? Mission analysis is about designing the orbit of a spacecraft in such a way that it can get there, stay there efficiently, fulfill its mission objective, and all of that without violating any hardware or safety constraints. And since the orbit of the spacecraft influences the design of the spacecraft and vice versa, it's a very iterative process, so you're basically never done. And also, since most spacecraft are still bespoke and every mission has unique requirements that will constantly change, especially in the early phases when you're not quite sure what you're doing, you want your software to be interactive, modular, and extensible. And when I say interactive, I'm not necessarily meaning a GUI, but also exploratory workflows like having a REPL or working with Jupyter notebooks and things like that. And it's also computationally expensive. So this is the most simplified form of modeling gravity. It's Kepler's equation, and as you can see, there's not a simple analytical solution there. So it's a transcendental equation. So already we need numerics, and we usually use this form, which is Newton's formulation of the problem. It's a second-order differential equation. So just to get started and just to model gravity, and of course it's not everything, we need to model the atmosphere, we need to model solar radiation pressure, even relativistic effects in the worst case. But before we even can start, we need an ODE solver, so a numerical integration, and then we stuff that into a numerical optimizer or do Monte Carlo simulations, so we're running this millions of times, potentially. It just needs to be fast. So great numerical performance is non-negotiable. Which means we have a trifecta of requirements. We want great performance, we want interactivity, and we want modularity and extensibility. And in the past, this was a pick-2 situation. So there's the big commercial GUI packages, which are reasonably fast, which are interactive, but it's basically you adapt your problem to their workflows. It's their way or the highway. And if you're not using the open source ones, it's horrendously expensive. And you can also go to a low-level library. So OraKit is the Java library I mentioned. Very good software, but it's also very low level. You're doing everything from scratch, or you use something in C++ or Fortran. And doing it every time again and again for every mission gets old really fast. Or finally, you could use Python and MATLAB. Python or MATLAB, you get interactivity and modularity, but you spend a lot of time waiting and drinking coffee, so not ideal. Which means a decade ago, roughly, I started asking the question, can we have our cake and eat it too? And my answer was an enthusiastic hell yes. So this is a comparative study of some micro benchmarks, runtime performance and lines of code relative to Fortran for some astrodynamics problems. We see that being less verbose than Fortran is basically table stakes. And the interesting thing is that if you look at Python and Julia, Python being a very dynamic language, but when you add a just-in-time compiler to the mix, you can get competitive performance, or use a language like Julia, which is designed around just-in-time compilation. Today, my answer is not hell yes, it's oh boy, it depends. So again, this leads to the question, what went wrong? And I promise I will talk about Rust, but it's easier to show what Rust brings to the table in comparison to the things where you're putting it in contrast to something. So why didn't we stick with Python? I will always have a soft spot for Python because my first programming language was MATLAB, being a mechanical engineer, and learning Python felt like acquiring a superpower. So learning a real programming language. But out of the box, Python is definitely not a high-performance language. And you can make it fast, but it's a really messy process. So you start out with some reasonably fast Python code, and then you have to ask, is it numerical? No, then you should probably use Cython to make it fast. Can you vectorize it? Yeah, then you vectorize your algorithm if you have the mental fortitude to learn about NumPy broadcasting rules. I don't, so I'm sorry. And then if you cannot vectorize it, you could use Numba, so the just-in-time compiler. And then if it's still slow, you can rewrite your hotspots in C or C++ or Fortran or Rust nowadays. But unfortunately, there's caveats with all of these things. So for example, when you use Numba, all of your abstractions go out the window. So the highest level of abstraction is a NumPy array or a list. And not having classes in a class-based object-oriented language, it kind of sucks. And rewriting hotspots is also not very fun to do because it's like whack-a-mole. You fix one thing, and then another thing becomes dominant and is too slow, and then you do it again and again and again. It's not a nice way of working. So in my personal opinion, you can do high-performance Python, but it's very hard to get an intuition about the performance of your program, and it's a lot of trial and error. So then, why didn't we use Julia? And this is much harder for me to explain because I used Julia quite a lot. Actually, I spent years promoting Julia and writing open source code in it, because it does make it possible to write code with native performance in a high-level language. And similar to Rust is, with Julia, you come for the performance and stay for the type system. So it's a real upgrade from your bog standard object-oriented programming going to Julia. So what's the problem? And a quick disclaimer, I have not followed Julia's further development closely in the past 2 years, so some of the issues I'm going to mention might have been resolved. But yes, let's put it in the words of Obi-Wan Kenobi. Like a lightsaber, Julia is an elegant weapon for a more civilized age. And in my words, and if you're not careful, you take your limbs off. So it is possible to write fast code in Julia, but it's also possible to write very slow code. So if you write Julia like you would write Python, there's a pretty good chance that you get Python-like performance. And I had a very hard time selling this to my colleagues, to engineers especially. So they said, why would I use Julia if I use it and then need to learn something new and it's still slow? So what's the point? So I give you an example. A thing that trips up beginners in Julia is type instability. So in a numerical code, you initialize a variable to some integer, because that's what it looks like in the paper, and then later you reassign a float to it, which you're allowed to do because Julia is a dynamic language. Unfortunately, then type inference panics and says, I cannot determine what this is anymore. The compiler will box it, put it in the heap, and your performance goes out the window. Or in a hot code path, you have an unexpected allocation because you used your vectors wrong, and then there's an intermediary somewhere, and your frenemy, the garbage collector, enters the chat. Also not great. And finally, what became the straw that broke the camel's back for me personally was, in my last big Julia project, the JIT overhead was starting to become a problem. So every time I ran my unit tests, the whole code base would be compiled. Every time we started up a new container in the back end, the cold start was really slow because everything got compiled again. And yeah, basically we would pay the compilation cost too many times because the compilation artifacts were not cached. So then, why Rust? In both Python and Julia, what I used was kind of a top-down approach, trying to achieve native performance in a high-level language. And Rust uses an opposite bottom-up approach. So instead of trying to make high-level fast, it's about making a low-level or systems programming language ergonomic and easier to use, pulling features down, so to speak, which convinced me to give it a try. And to be honest, when I looked at my shopping list of features, there wasn't exactly a wealth of alternatives. So yeah, I put expressive type system first because I believe that if you have a better domain model, it makes your software easier and safer to use. And I'm lazy. I don't want to do the bookkeeping when the compiler can do it for me. So that's important. And also in the past years, I was radicalized by the functional programming task force. So once you use something like algebraic data types, it's very hard to go back to not having them. And excellent tooling. I think the effort that has gone into Rust tooling has pushed the whole industry forward. So Ephemerista is primarily a Python project, and until a few months ago, it was just horrible working with the tooling and setting up the project and getting everything to work together. Fortunately, there is UV by Astral right now, which is written in Rust and heavily inspired by Cargo. So kudos to them, because this made it bearable to work with Python. But yeah, as I said, it's inspired by Cargo, and all the tooling out there, or a lot of tooling out there, is inspired by Cargo, and it's just that good. So another thing I want to have is operator overloading. Not the crazy kind, just basic arithmetic operations, but I want my vector math to look like math and be easy to parse visually. And I mean, this ruled out languages like Zig, for example, because they have a stance of not providing that. And Rust strikes a nice balance there, I would say. So portability and small runtime. This ain't my first rodeo. I tried building a reusable astrodynamics framework in Python, in Fortran, in Julia, and quite frankly, I'm done. I don't want to do it another 3 times. And writing it in Rust means I can run it in the browser, I can run it in the back end, I can call it from Elixir, I can call it from Python. And I do not force people to download LLVM or a JVM just to run my code. That's a plus. Not going to spend much time here. It's the killer argument, memory safety without GC. I'm also done debugging memory problems. Don't want to do it anymore. So the big question mark, the final one, is interactivity. Obviously, Rust does not have a REPL, but when I found Py03, and being able to write a Rust module in a Python module in Rust in an hour, and it being that easy, that pushed me over the edge. So yeah, basically we said, let's try this out, let's go ahead. We're going to cheat, and we are going to write a big Python library without writing a single line of Python. We're going to do it all in Rust. And the result is LOX, an MPL licensed set of crates for astrodynamics applications. At the moment, we provide timescale and reference frame transformations and some cool analysis tools, such as a parallelized path predictor, which allows you to predict when your ground station is going to see your satellite, or in a constellation, all of the satellites. And it is still early days, and things are highly experimental at this point, so I do not take responsibility if you crash your spacecraft. So please have a look at our GitHub repo and tell us how we're using Rust wrong and what could be improved. That would be much appreciated. And at this point, I also want to give a shout out to Nyx, NYX, which is the OG Rust astrodynamics crate, which is much more mature and has actual flight heritage. So please also check that one out. So why LOX? The pun was too good to resist. So liquid oxygen, abbreviated LOX in the aerospace, submarine, and gas industries, is the liquid form of molecular oxygen. It was used as the oxidizer in the first liquid-fueled rocket. I'm sorry. Emphasis mine. I do want to give a motivating example about how we use Rust to write better code, but I also don't want to go into the weeds too deeply because time's ticking. If you want to know more, there was a talk at Rust Week by my collaborator Angus Morrison. Excellent talk, have a look at it. Tiny bit out of date, so we changed a few things in there, but still a recommendation if you want to go deeper in what I'm going to present now. So the example I put here is the zoo of timescales we have to deal with in astrodynamics. So I think everyone knows UTC and TIE, and maybe UT1 rings a bell, so solar time. But then we have also this corner below here, which is relativistic timescales, and then it gets funky. But we have to use most of them. And we want the compiler to know in what timescale we're in, so we're not getting into the situation where we're passing a timestamp into some lower level routine and expect it to be in barycentric time, but actually it's in atomic time. So we're using generics quite heavily. So here, this is our time struct, which is parameterized with the timescale, and it has an offset, which is just a time delta to some epoch. In our case, we're using January 1st of 2000 at midnight, just because it's the convention. And if we look at this time delta, then this is an enum, and what we're doing is we're measuring seconds since this epoch, and then attoseconds from this second to get a lot of precision in there. And since we're having two ints, and we also need to be able to convert to this time delta from a float, we have some edge cases like positive infinity, negative infinity, or not a number, and we want to be able to represent them without panicking, without using any funky sentinel values like that. And yeah, some types, they're like magic. No, they're not, but they're great. So they make my life a lot easier. And then finally, we can use this to convert between timescales. And for that, we have a trait called offset. So this is the infallible version. We also have a fallible version where you get back a result if something can go wrong in the conversion. But we're saying we're going from an origin timescale to a target timescale, and since some of the transformations actually depend on the time in the timescale, we're passing in the delta, and we're getting another time delta out, and then we can add things together, and everything is quite seamless. So from the user perspective, they have a timestamp somewhere, and they're calling to scale, and they don't need to care about the rest. But it leaves us open to implement new timescales. So for example, there's a lunar timescale in development right now, or when Elon finally makes it to Mars and leaves us alone, then they probably have some sort of mass time, and we can handle it. Hold that thought. I'm going to mention something about this in another slide. So the other question is, why should you not use Rust for this? And so I'm not actually a software person by training. I studied mechanical engineering and then went off the rails into this stuff. And it's good that I've been able to translate between the different camps. So aerospace engineers on one side and computer scientists and pure software people on the other side, because there's a lot lost in translation between them. And to the aerospace engineer side, Rust might be a bit intimidating, because it is a complex language and there is definitely a learning curve, so I'm not going to dispute this. But I am going to argue that it's just different, and if you approach it with beginner's mind, and especially when you're experienced, you will have a better time than just barging in there and trying to implement linked lists. So in short, don't panic. Sorry, pun intended again. But maybe actually do panic. So unwrap all the things, clone all the things in the beginning, don't implement linked lists, it's going to be fine. You can learn about the other stuff later, and then it is a really ergonomic and easy to use language. So I'm probably preaching to the choir here, but this is for the folks on YouTube. But there are some missing features or areas for improvement for this scientific computing field. Also, I'm not saying that it's impossible or it's not there yet, especially if you look into crates or you look into nightly, but it's not as frictionless or seamless as I would like it to be. So this might be a me problem, but I'm coming from Julia, and Julia is specialization, the language. So the compiler specializes all the things, and the lack of specialization in Rust always trips me up. So it's the way I approach problems is often that we have a very generic implementation of something which is not very optimized, and then you drill down into more specific implementations. If some preconditions are met, which ideally would be traits, but then very often the compiler complains to me about conflicting implementations. And I use macros as a workaround for this, and it's fine. I just really would like to have specialization. The next thing is linear algebra and multidimensional arrays. There are crates for that, but if you look at MATLAB or Julia, one of the strengths is that the multidimensional array or tensor types are part of the core language. So you're not having discussions about, should we support an algebra, should we support ND array, or both, or some other library, because there's a standard. It's easier to collaborate on these things. So I hope that something crystallizes in that direction, so we can don't need to support all the things. What would be nice to have is automatic differentiation, and it's already there in unstable, so I'm really liking what the enzyme folks are doing. I just would like it to be stable. And my final point is heterogeneous computing. So in Julia or Python with Number, it's very easy to move from the CPU to the GPU. You just pass in a GPU array to your algorithm instead of a CPU normal RAM-backed array, and everything mostly works in many cases, not all the time, but in many cases. I haven't seen any good solution for Rust there yet, so if you know about something, please tell me. I would like to know how to do that. And yeah, I'm done with complaining. So what's next for LOX? I was hired by KSAT from Norway, and I'm going to help them build a new system which is going to do mission analysis and much more in Rust, using LOX, making LOX ready for production, so you can in fact use it to fly your spacecraft. The way we're doing is we're employing a sort of strangler pattern. So what I'm working on right now is wrapping OraKit, this Java library from Rust, so we can fill in all the bits and pieces that are still missing and gradually then get rid of the Java stuff more and more until it is only used for validation. I've also have some ideas about using Bevy for visualization, which is going to be a cool thing, I believe, because it's also important to visually see what's happening with your orbits. And with that, I'm done. Thank you for your attention. You can find me on GitHub, and I will take your questions.
Thank you, Helge, for talking about Rust in space. We're going into the panel very quickly, but I have time for one question. Or you can take it into the lunch break. I'll take yours and then.
So originally you said that you would not be held reliable for me using LOX, and now you're saying that you are preparing it to be ready for production, while still keeping it in open source, I guess. So what do you need to do in order to do that? I mean, as you pointed out earlier, you just have one shot usually, right? So it has to be correct. It has to be, I don't know, peer-reviewed or whatever. So it also sounds like quite a niche market to me. So who's working with you on that? How do you do that?
So it's an open question how you do validation of these things. And the way we've been doing it in the past is we're putting the same inputs into different software suites. For example, we will our timescale transformations, we compute them with LOX, we compute them with ORCID, we compare the results, and if they match reasonably well meaning ignoring any differences in floating point math libraries, things like that, so with small tolerances, then we're fine with that. Or for example, the pass predictor I talked about, we're getting the exact same results like NASA's GMAT. And in terms of validation, this is really the best we can do. And once we have this level of confidence, we can look into formal verification and maybe having external parties have a look at it and see if it does what it's supposed to do. So that's the plan right now.
Okay, thank you, Helge. Other questions for Helge? Take it into the lunch break. And thank you so much for talking at Oxidize.